Okay, so let's give this a try. These are the notes for section 4.4, and this is the material that we were going to cover in class on Monday the 16th. So we're going to talk about concavity and the second derivative test. Now remember, in this chapter we're seeing all kinds of procedures for just about everything. You know, we've talked about, I guess we've seen Rolle's theorem, we've seen the mean value theorem, we've talked about there's just a process for finding what a critical number is. Recently, we've talked about the process for finding when a function is increasing or decreasing, and we also called it the first derivative test, which is related to the idea of finding relative maxes and relative mins. And in this section, you're also going to see we're going to be talking about a procedure for concavity, and we're going to talk about something called the second derivative test. And so, as I mentioned in class, I highly recommend that you have note cards or summaries of all of these procedures, and it definitely looks like you're going to be tested on chapter 4 just through WebAssign, but still get yourself organized now so that you can be pretty comfortable with using those procedures and things like that. So anyways, definition of concave up and concave down. So at first, concave up and concave down seem pretty simple. Concave up, it's kind of like opening upwards for your function. Concave down, it's like you have a function that's opening down. Now, just because it's opening up and opening down does not necessarily make it concave down. It doesn't have to be completely like U-shaped in either direction. Even something like this would be concave up, and something like let's see, you could have concave up like that. I guess you could have concave up like this as well. So you could have an increasing function that's concave up, and you could have a decreasing function that's concave up. And then concave down, you could have a piece that goes like that, and then likewise you could have a piece that goes like that. So a lot of times when I think of concave up and concave down, it's kind of weird, but I think of the idea of holding water. Like if I were to pour water over the top of this, you know, when it's opening like this, you would hold water in the inside, but when it's shaped like this, if you poured water over the top, it would kind of roll off the side. So that's concave up and concave down. Now, we'll talk about the calculus definition of those in just a second. But first, let me also define points of inflection. Now, points of inflection are simply points on the graph of a function where the concavity changes. And so we've recently talked about what did we talk about? We talked about relative maxes and relative mins. Those are places where the function's changing, and critical points, those are critical places where things are happening. Well, these are also key places on functions, these points of inflection. And so we're going to get into the math of this now, and we'll run through a number of examples and all of that. But essentially, it's the point where the concavity of a function is changing. Okay, so from a calculus perspective, what is the relationship among f, f prime, and f double prime based upon concavity? I like to think of it like this right here. So I always draw this picture, and I'll explain what I mean by that. And then I draw another picture. It looks like this. This is pretty much where we all are right now with what's going on in the world. But in relation to concavity, this is a concave up function, so let's say that our function f is concave up in this picture. And when f is concave up, the big definition is this. Look at your slopes of those tangent lines here. So what's the defining feature of this is the slopes of those tangent lines go from negative, and then less negative, and then 0, and then positive. So the slopes are increasing. It's really important to notice that. So the definition of a function f being concave up is that the derivative of f is increasing. I'm not saying the derivative is positive. Look at the derivative here is not positive. It's negative and less negative, and then 0. I'm saying the derivative or the slopes are increasing. So you can see those slopes are increasing as they go from left to right. But in last section, we learned that when a function is increasing, its derivative is positive. And so what is the derivative of f prime? Well, the derivative of f prime is f double prime. And so when a function f is concave up, f prime is increasing and f double prime is positive. And so this is hopefully going to get you thinking that, okay, maybe when we're talking about concavity, we need to start analyzing the sign of f double prime. So last section, we were doing some f prime analyses where we were trying to determine when functions were increasing and decreasing, but in this section, we're going to be doing a lot of f double prime analyses. So in this picture, very similar. When you have a function that is concave down, let's look at our slopes. So we have a positive slope, less positive, 0. Now it's a negative slope and it gets more and more negative. So our slopes themselves are decreasing. And we know that when any function is decreasing, in this case that function is the f prime function, its derivative is negative. And so this is a really important connection to note among f prime, and f double prime. And so one of the other things that we should really chat about in the beginning of this, whoops, let me back that up just a little bit, is let's talk about the inflection points in applications. And this is where concavity actually does have some relevance. And so a classic application of where we would deal with concavity and inflection points would be in a business example like this, where on this axis we have maybe the expenditures for a business, and on this axis we have profits. And so what we often see is we see curves in businesses like this, where we see as the business spends a little bit more money on employees and resources and things like that, you know, they can potentially try to optimize their profits and increase their profits. And so a lot of times we see that there's a positive rate of change there, where you know, the slope here is some positive slope, but then that slope is going to increase, and businesses love that because that means that they're getting more profit for a smaller change in expenditures. But then sometimes what happens is with businesses is there is a point where the concavity changes, and you can kind of see here that we're going from concave up in this section to concave down in this section. So this place right there, that would be our point of inflection, and from a business perspective, that is what we would call a point of diminishing returns. And so you could see their profit is still increasing. You know, the company, some people or some companies might say, hey, our profit is still increasing, so let's keep spending more money, let's keep hiring more employees, etc. But then other people might say, you know what, we're not getting as much profit for our expenditures as what we were before, because at this point your slope, the change in your profit for a change in expenditures, is much greater than it is at places like this. And so that point of diminishing returns is a point of inflection. We see that all the time in business applications. Okay, I'm going to stop this video here, and in the next examples I'm going to walk you through the process, which is going to be the key process in this class for discussing the concavity and finding points of inflection for a function.